Problem 419 on page 191. To start, let's recall back our from Physics 2 that the capacitance of a gap parallel plate capacitor is given by epsilon naught A over D. The question gives us two scenarios. One in which, in both scenarios, half of the gap of the capacitor is filled with a dielectric material, dielectric constant epsilon R. For part A, this dielectric fills it the entire area, but only half the distance. And in part D, it fills the entire distance of half the area. So let's see what we can do about this. So for part A, it fills the entire area for half the distance. I'm going to assume the same free charge distribution as with the empty case. In other words, the two plates have the same charge as they did before. And that will create electric field, which will create a change in potential both inside the dielectric material and inside the air. For the air, the rate of change of potential is the same as for a capacitor with no dielectric material. It's just sigma F over epsilon naught. We multiply this by the distance that it travels half of the distance between the plates, d over 2. And remember, the free charge density is Q over A. That gives the potential difference because of the air part of the capacitor is this. Now when entering the dielectric material, the electric field and the rate of change of potential needs to follow this formula right here. Now, one thing that really helps us, this is again the free surface charge density. There is no free charge at the boundary between the air and the dielectric. All of the surface charge is bound surface charge, which means that this quantity, epsilon times dV dN, should be the same in air as in the dielectric material. In air, epsilon is epsilon naught. In the dielectric material, epsilon is epsilon naught times epsilon R, which means that the rate of change of potential inside the dielectric material is equal to the rate of change of potential in the air divided by epsilon R. If you recall, that rate of change was sigma F over epsilon naught. So the rate of change of potential inside the dielectric material is sigma F over epsilon naught epsilon R. That too happens over a distance of 1/2 d. And so the potential difference is d over 2 times q over epsilon naught epsilon R A. To get the total potential difference between the two plates because of these two materials, we take this potential difference and this potential difference and add them together. Notice that they are very, very similar. The only difference is there's this epsilon sub R here and nothing there. So we can pull out their similarities, dq over 2 epsilon naught A times 1 plus 1 over epsilon R. Now let's go back to our definition of capacitance. Capacitance is equal to Q over V. So Q divided by this V right here gives us this formula here, 2 epsilon naught A over D times 1 plus 1 over epsilon R. If you recall that the original capacitance was just epsilon naught A over D, we have an epsilon naught A over D. We can pull that out, call that the original capacitance, and say that the original capacitance changes by this factor, which I did a bit of algebra. So it changes by a factor of 2 epsilon R over 1 plus epsilon R. As a side note, since epsilon R is always going to be greater than 1, this capacitance is always going to be greater than the than C naught, than the capacitance without any dielectric material. Scenario B. This time, the capacitor is again filled halfway with a dielectric material, but the dielectric material does stretch plate to plate over half of the area. So for this one, I am going to assume the same potential difference as in the original capacitor. And I can do this because there is never going to be a boundary where this matters, because the boundary between air and dielectric material is horizontal in that picture, but the potential is changing in the vertical direction, so this is always going to be 0. Also, because we can assume things are fairly linear, we can say that this quantity dV dN is equal to the total change in volume divided by the total distance between the two plates. For the half of the capacitor that does not have a dielectric material in it, we can then say that dV dN is equal to sigma F over epsilon naught. We can do this, we can solve for charge. Remember, charge is sigma times A. So move the epsilon here, sigma times A, or dV dN times epsilon times A, gives you that charge on the free half of the plate. For the half of the plate that has a dielectric material in it, we still have a similar relationship, only now it's sigma F over epsilon R times epsilon naught. We can again calculate the charge on that half of the plate, solve for sigma F, multiply by the area, which again, remember, is 1/2 of the total area, and we get this is the charge on the dielectric half of the plate. To find the net charge, add these two together. Again, they are very similar, differing only in that this one has epsilon R. Put them together, you get this is the total charge. Again, we use the definition C is equal to Q over V. So we have Q over here, divide by V, that just means we get rid of that. And we get that capacitance is epsilon naught A over 2D times 1 plus epsilon R. Again, C naught is just epsilon naught A over D. We pull the epsilon naught A over D out, call it C naught, and we see that C naught is multiplied by the quantity 1 plus epsilon naught over 2. Again, epsilon naught, that should not be epsilon naught, that should be epsilon R. Epsilon R, the relative permittivity, is always greater than 1, so this quantity is going to be greater than 1, which means capacitance again increases. One thing that we can deduce from this is that no matter the situation, putting a dielectric material inside a capacitor will increase its capacitance.